This video will explain resting membrane potential and the events at the neuromuscular junction. As you can see, I've drawn a phospholipid bilayer representative of the plasma membrane. On this side of the membrane is the extracellular fluid. On this side of the membrane is the inner contents of the cell where we have the intracellular fluid. Just next to the membrane, we find that there is a greater concentration of sodium ions outside the cell compared to that inside the cell. We also see there is a greater concentration of potassium ions inside the cell compared to potassium ions outside the cell. Because of the electrical differences and the number of charges outside the cell compared to inside the cell, the membrane develops a charge which can be measured in millivolts. The charge on the sarcolemma of skeletal muscle fibers measures at -90 millivolts. Let's take a look at what happens when an action potential or electrical current from an axon meets the sarcolemma at the neuromuscular junction. Here we have an axon splitting into little branches called telodendria, forming expanded ends called axon terminals. When an action potential comes down the axon telodendria to the axon terminal, remember that an action potential is an electrical current. This current, when it meets calcium voltage-gated protein channels, will change their shape, allowing them to open. At that point, calcium comes into the axon terminal. The influx of calcium triggers synaptic vesicles in the axon terminal containing acetylcholine to fuse their membranes with the membrane of the axon terminal, allowing acetylcholine to be released and diffuse in the synaptic cleft. From there, it will bind to acetylcholine receptors. When acetylcholine molecules bind to acetylcholine receptors, that bond changes the shape of the protein receptor, which then acts as a channel. Now, sodium can diffuse down its concentration gradient into the cell, and potassium can diffuse down its concentration gradient out of the cell. Because more sodium diffuses in than the amount of potassium leaving, the membrane changes its voltage. It goes from -90 and becomes less negative. That change at the motor end plate is referred to as an end plate potential. The end plate potential starts an action potential in the sarcolemma by spreading to the other areas of the membrane that are next to it. As that change in voltage spreads on the sarcolemma, it causes an opening of sodium voltage-gated channels, which will open up, allowing sodium to come in, causing depolarization of the membrane up to +30 millivolts. At +30 millivolts, two things happen. Sodium voltage-gated channels close, and potassium voltage-gated channels open. Since sodium came in, we went from -90 millivolts all the way up to +30 millivolts. At +30 millivolts, when those potassium voltage-gated channels open, potassium can now leave the cell. As the positive potassium leaves the cell, it takes its positive self out with it, making the membrane more negative again, restoring it back to -90 millivolts, at which point, those potassium voltage-gated channels will close. This depolarization and repolarization of the sarcolemma is what is known as an action potential. Again, you could think of this as an electric current that spreads along the sarcolemma all the way down the transverse tubules, at which point I've made another video for you to see what happens then.